Alright, so I will go ahead and get going since we're a little past 4:30. I'll start with logistics for the exam since it is the first one of the semester. So exams are typically anywhere from about 10 to 12 questions, and it usually splits about one-third conceptual and two-thirds calculation. In this class, because there's a lot more concepts involved compared to Physics 1, sometimes it can lean more like 40 points conceptual, 60 points calculation, but still somewhere in that ballpark. So conceptual are always multiple choice, just like on the quizzes, and conceptual questions are very similar to what you'd see on quizzes. Calculations are most similar to what's in the practice question packet, and we'll look at some of those types of questions in a bit. Second most similar to what's in the notes as far as the level of difficulty. So homework is meant to be harder than the exam questions, so that by the time you hit the exam, it shouldn't feel as bad if you've been doing well on the homework and spending some time on those questions. You can bring a cheat sheet, and it can be one side of an 8.5 by 11 sheet of paper with whatever you want to put on it and however you want to put it on there. You can write really small if you want. You can print it out, type it all up, print it out. You can take a bunch of pictures from the notes and then resize them to the size of an 8.5 by 11, whatever you want to do. Does not matter to me. What I would recommend, though, is a cheat sheet is really meant to help you study for an exam. It's not meant to be your lifeline when you get to the exam. Usually, if you approach it from that direction, you run into problems because the problems you see on the exam aren't a perfect match for what you're seeing on your cheat sheet, and that's intentional. It's an exam is meant to check whether the content makes sense, not just whether you happen to have the right thing on your cheat sheet, but it is something that can help if you get a little stuck in places. So treat it like that, and it will go fine. Now I'm going to do a quick recap of chapters 18 and 19. That's all that's on this exam. I'm seeing that I left out this blank right here. It's just supposed to be charge. It's probably clear from context now, but electric charge. So for chapter 18, the main concept stuff, I would say, is things like on really the second page. The first page is kind of early observations that probably you don't have a lot of trouble with. This one is where it can get a little tricky, and that's knowing whether something is positively charged because you removed electrons or negatively charged because you gained electrons. That can get mixed up a lot. So that's a potential concept type question. Another type you could see is something related to induction. So just remembering what induction is. It's the idea that even if something doesn't have an overall net charge, meaning it's neutral on the whole, if you hold something charged up to it, it will still attract the uncharged object because holding that charged object up to it separates out charge on the neutral object. And the net force that acts on it as a result is always attractive for induction. I could ask a question where I end up asking something like how many electrons does it take to make up such and such amount of charge? That would usually be as part of a larger question, so something about maybe forces between objects, something like that. I don't really consider this an equation in the sense that it's just saying whatever charge you find is always a multiple of the electron charge. We can write that as an equation, but it's sort of just a statement of quantization of charge. If that idea is not clear, like if I give you a certain charge, like 5 times 10 to the negative 7 coulombs, or some other random number, can you tell me how many electrons that is? All you have to do is see how many times the electron charge goes into it. Just like if I told you the mass of the Earth and I told you the smallest mass you can have is the mass of a certain pebble, could you figure out how many pebbles make up the Earth's mass? It's the same kind of question. You could treat it as math as you want. I kind of just think of it as, I don't know, that's something built into our brains that can figure stuff out like that out. Coulomb's law is the other big calculation thing for this early part of the chapter. Because we spend so much time on electric fields a little bit later, I'm not going to stress Coulomb's law beyond one single question, and it would be something either like this, where you're just finding the net force on a charge due to two other ones, and that's just along the same line, so not one as complicated as this one. I'll save something for something like that for electric field based calculations. But this one right here, you could expect something like that, where the charges are along the same line, or even just two charges and you want to find the force they exert on each other. Straightforward Coulomb's law stuff, but you do need to be able to do those calculations, get those exponents and stuff right. All right. Electric field is the big one for the chapter. It's the thing that takes up the whole rest of it. So, you need to know what an electric field is. It's this thing created by every charged object at every point in space, even if there is no other thing present. And so I get questions a lot like, if we look at this problem, people will ask, what kind of charge is at O? And the answer is there isn't any. That's the point of the electric field, is it exists even if nothing's at O to feel or interact with that field. But to get the direction of the field right, you can pretend there's a little test charge there. You take out your measurement tool and hold it up right there and see what happens to it. And that gives you a sense of the electric field. But the electric field exists solely because these other charges are around that point. And the little positive test charge is just a way to measure it. So, conceptually, it's the idea that the electric field exists because of a big charged object, but you can measure it with a test charge. How you do that is you measure the force on your test charge and divide by whatever test charge you used to get something that doesn't depend on the measurement tool you brought. Just depends on what is creating that field in the first place. That's why we define the electric field this way. For calculations, the main ones are like this. I can guarantee you there will be a question like this on the exam. And so just make sure each of these steps is comfortable. The homeworks had several like this. If those are fine, you are fine. If those are not fine, take a look back at those. We'll look at some examples later. And then if you happen to know the electric field, can you figure out the direction and size of the force on a charge when you put it into that field? So, once you've done all that work to figure out the net electric field, if I say place an electron at the point you found the electric field at, can you find the size and direction of the force on it? How you do that is you multiply by the charge of the electron. That'll give you the size of the force, the magnitude of it. And for the direction, you use these rules. So the force is opposite the electric field direction if it's a negative charge, which would be the case for an electron. It's in the same direction if the charge you're putting there is positive. That takes up a big chunk of chapter 18 already, as far as points go. There could be a single question about field lines. This question captures all the things you really need to know about field lines, which is the more charge you have, the more field lines that charge should get. Field lines leave positive charge and enter negative charge. And how close the field lines are is telling you something about how strong the electric field is at each point. For Gauss's law, it's going to lean heavily conceptual, meaning more multiple choice type questions, because calculations with Gauss's law are kind of tough. The only calculation you can expect to do, maybe, is one like this very last question, which the homework had, and I believe the practice had one like that as well. So the only calculation you would ever have to do with Gauss's law is something like this. Concepts-wise, just knowing what Gauss's law says. And it relates the flux through any surface, any bag you choose, and that's the flux is the amount of field lines passing through that bag, to the charge that's inside the bag. So what's happening on the surface of the bag tells you something about what's inside the bag. Vice versa is true as well. So maybe an example of something like that seems tricky, but is actually an easy question. Say I've got a little charge in the middle here. This is like 3 separate cases, a little charge Q. But in this last case, I also have a neutral shell around that charge. I'm going to draw 3 separate Gaussian surfaces. And I might ask you something like, rank the flux through each of those surfaces. You know, is one going to have more flux to it? Is one going to have less? That's the question. Oh, and then, sorry, between case 1 and 2, it's kind of hard to tell how they're different. Let's say for case 2, it is a larger Gaussian surface than case 1. So you might look at that and say, well, the bigger Gaussian surface is going to have more flux through it. But what does Gauss's law say? It says the flux is always equal to the charge enclosed by your surface over epsilon 0. I'm enclosing the same amount of charge in all 3 cases. It's whatever that charge is at the middle, because the shell in this last one is neutral. That means the flux through all 3 surfaces is exactly the same. That's a direct application of Gauss's law. So questions like that. I think that is the main stuff for chapter 18. If you see a shell, you just need to use the electric field of a shell instead of the electric field of a point charge, but those equations are given. Same for a capacitor. And then this summarizes everything you need to know for this last section, the properties of conductors. Chapter 19, potential. Remember, it is just a different way of looking at charges. It's an alternative to electric fields. They're complementary to each other. You can kind of jump back and forth between them if you want, but it is just a different way you could approach looking at charge. In order to understand the idea of potential, use the analogies in this chapter. They are really one of the most important takeaways to get the concepts down for potential. So this page, I'd say, is one of the more important ones in the chapter. Potential is like the height of a hill, electric field is like the slope of that hill, and everything else we talk about in this chapter pretty much follows from those 2 ideas. For instance, positive charge likes to go downhill, negative charge likes to go uphill. And really, for any situation you're looking at, picture what a rock would do on a hill. That's what positive charge does. Negative charge does the opposite. So for instance, if a rock is sitting on a really steep part of the hill, it'll feel a large force and move pretty fast. So will a positive charge if it's in a region where it is a large electric field. And it will go from the top of the hill to the bottom, go downhill, high to low potential. Negative charge does the opposite of those things. Then with this KQ over R, you can expect to have to jump to finding the potential due to a group of charges. So I won't have you calculate the potential for a single one, you'll have to calculate it for a group. For that, you just have to remember, you don't do vector stuff for potential, you just add. So for V, you add, for E, you use vector addition. Properties of equipotentials are pretty common conceptual questions. So do you know when a charge is going to slow down or speed up depending on the equipotentials it's moving through? Calculation-wise, you can expect one like that, conservation of energy stuff. It goes the same way every time. So if you follow this sort of procedure we followed in part C, it's that way every time. And you won't need this page. For capacitors, the big thing to remember, and the big thing that got a lot of people on the quiz today, is this. Capacitance does not depend on charge or voltage. So if I change either of those things, I am not changing the capacitance. The only way I can change capacitance is if I change the size of the plates or put a dielectric in between. That's the 3 things we looked at here. What happens to charge and voltage is that if one of those doubles, the other doubles because capacitance doesn't change. It's relating charge to voltage, and so if one doubles, the other has to double to keep up with it so that their ratio, the capacitance, never changes. Calculation-wise, it's pretty much just always a combination of this equation and then the one that comes from up here, Q equals CV. You just smash those together in several different ways, and that's always how the calculation problems go. These questions are good conceptual questions, and you won't need the last page for this exam. Okay. Questions on chapter 19. All right, well, if not, I did have one person email in a question, and so I'll go over that first, and then if you have other questions from the practice exam stuff, we can look over those. There are solutions for each question, but if any of them weren't clear, I'm happy to go over them in more detail. So this was a question for one of the homeworks. We've got 2-point charges on the y-axis. This one up here is negative, this one's positive. They're the same distance from point P. We want to know the net electric field at P, and then if we put a little charge there, what happens to it? So we'll start with part A. To do it, we're going to go through that procedure that we see in the notes, which is, come back to chapter 18, because it's asking about the net electric field. It's these steps here. So step 1, I need to draw my field vectors. Step 2, find the components. Step 3, use kq over r squared. And step 4, do the rest of the vector addition stuff with trig. So step 1, I need to label my electric field vectors. To do that, it can be helpful to pretend there's a little positive charge at point P. And we ask what would happen to it, which way would it feel a force. That is also what we define to be the direction of the electric field due to each charge. So Q1, it would attract that little positive charge. And so we say the electric field due to charge Q1 points towards it. Meanwhile, Q2 would repel a little positive charge sitting at P. And so we say that is the direction of the electric field due to charge 2. Now we need to do vector addition with those. So we've got 2 vectors that we need to find the x and y components of. In order to get the net electric field that they produce. All right, so on my picture, I'll label my components so it's clear what signs I should use, SIGN. E2 goes to the right and upward. E1 goes to the left and upward. So E1 will have a negative x component because it points to the left, positive y because it points up. E2 will have a positive x and positive y because it points to the right and upward. Then it'll be the magnitude, the size of the vector, times either sine or cosine. If the vector's totally along the x-axis, then it would have 0 y component. Vice versa, if it's totally along the y-axis, in that case you don't have to worry about sine or cosine. But here, they've got a little bit of both. So I need an angle to work with to say whether I use sine or cosine. If this angle's 30.6, so is this. And they tell us that this angle over here is. So I see that if I'm looking at the x component of, say, E2, it's adjacent to that 30.6 degree angle. If it's adjacent, I use cosine. That means the other one is sine, because it's opposite. I do the same for E1. If I look at this component, the x component, it's adjacent to that 30.6 degree angle. So I use cosine. Let's say use sine. And so my net x component is E2 cosine 30.6 minus E1 cosine 30.6. And then in the y direction, I add the 2. All right, from here, either I could do a decent bit of calculation, or I can be a little bit clever as far as looking at my diagram and realizing there's some symmetry happening here. So charge Q1 and Q2 have the same value, just opposite signs, and they're both the same distance from the point P. That means if I calculate their electric fields, or field strengths, the magnitude of those fields, I'm going to get the same number for each. Because it only depends on those things. But that means that whatever x component I get for E1, I'm going to get the same number for E2, just positive instead of negative. And that means my x components are going to cancel out because they're in opposite directions but have the same size. So even without calculating, I can tell the net x component is going to be 0 for this electric field. For the y component, because E1 and E2 have the same size, I know I'm just going to get double whatever I calculate for one of them. What I mean by that is, I could just calculate E1 sine 30.6 and double it. That'll still give me the same numbers if I calculated each one separately. That's for this specific problem, but if you can find tricks like that, it'll just shorten things a little bit. So now let me calculate E1. For that, I'll just come down here with it. E1 is K. Absolute value of Q1. I use absolute value because I already dealt with the signs, positive or negative, based on the directions of my fields. So I don't want to do that, or double count the signs. If you're hearing the dogs going crazy, I'm sorry about that. The distance is in our picture. It's 0.88 meters. Can we square it? Oh, the charge was itself negative. We're taking the absolute value, so it doesn't matter, but Q1 was negative. All right, if I calculate, I get 48,758 if I round at the last decimal place. And so I come back up to my x and y components. I know that my x component is 0 for this problem, but I could still calculate this if I wanted to be certain of that. For my y component, it's going to be, whenever this goes away, it's going to be 2 times this number I just found, and then sine 30.6. So 639.4 newtons per coulomb. And I could stop there and realize, okay, that's the entire electric field, the net electric field. Because, again, the x components cancel, the y components add. So my net field looks something like this. We could get that with the parallelogram rule for vector addition as well. But if you want to keep it general, like what you would do for any problem like this, what we would do next is say Pythagorean theorem. And then when we put those numbers in, we'll just happen to realize, oh, we just get whatever we had for the y component. For the direction, does it ask for direction? Oh, it asked for the magnitude, so I'm technically done with part A. But if I wanted direction, I could either go through the inverse tangent stuff. Again, if I wanted to keep it general. If you're dealing with like something pointing along the y-axis, though, you'll get technically infinity for this because it's telling you the slope. Or it depends on if the calculator's okay with the dividing by 0 stuff. But really, we can tell that the angle is 90 degrees from our picture, that E net makes a 90-degree angle, or I would just say it's in the positive y direction. So in general, you would calculate this to find that angle, but for this particular problem, I can just see from my picture it's in the positive y direction. All right, and then part B, it says if I release a small positive charge from that point, from point P, what will its acceleration be? Well, if I put a charge at that point, the force on it will be equal in magnitude to the size of the charge I put there times the electric field strength at that point. The size of the charge is 8.7 microcoulombs. The electric field strength is what I found in part A. That comes out to some number, but I need to find the acceleration. That's what they ask for, the magnitude of the acceleration. So I need to relate this force to an acceleration. Well, Newton's second law is still perfectly good for that. It's equal to the net force, which in this case is just the electric force on that charge, divided by its mass. And the mass is 1.15 grams, or 1.15 times 10 to the negative 3 kilograms. The force is, if I calculate, about 0.4 newtons, 0.43. So something like 375.5 meters per second per second. And if I want to know the direction of the force on it and the acceleration, remember the force is going to be in the same direction as the electric field. So if I put a little positive charge at P, it'll feel an upward force there, one in the plus Y direction, and so its acceleration will be in that direction as well. It'll shoot off that way. All right, so questions like that are tedious, but it's the same process every time you do these kind of problems. Okay, if there aren't other questions, maybe the last thing I'll do before we call it a day, unless questions pop up, is to go over some of the stuff that was on the quiz from today. I won't say specifics because there are some people who have not taken it yet, but I will say the quiz did not go well, and it happens a lot on this chapter because it is a big pivot from chapter 18. But for the exam, that means you'll want to look over some of these concepts more. The grade you see in Canvas is 1 point higher than what you actually made on the quiz because it did not go well for the whole class. So when that happens, I usually say, okay, if no one did that well, it must be me, and so I give a little curve point, and that's what happened here. So everyone got an extra point compared to what you actually scored on the quiz. That means we need to look back at some of this stuff. So, chapter 19. First is what is potential in the first place. So, electric fields, we spent a long time on and said they are the force that a charge feels divided by the size of that charge. We have something similar for potential, but it's not the same. Instead of force, it's potential energy divided by the charge, that the whatever charge you're placing at a certain point. So that charge has a certain potential energy. When you set it somewhere, you divide by the size of the charge you're setting there. That's what we call potential. That's our definition right here. Then there's the difference between how you find net or total electric potential and net electric field. Electric fields add like vectors. You have to do vector addition, and that means you can have some cancellation happen. Potential just adds. So if you've got 4 things that are all creating a positive potential, the overall potential is positive as well. It's just regular addition. Then it's things like, what do charges like to do? Negative charges like to go uphill. Positive charges like to go downhill. That means any negative charge you see will go from low to high potential. It'll head in the direction of wherever higher potential is. Positive charge will go, naturally at least, in the direction of lower potential. If you force it to go the opposite way, it'll slow down, eventually come to a stop, turn around, just like rolling a ball up a hill. If you try and force it up that hill, it'll go for a little bit, but then slow to a stop, turn around, roll back down the hill. That's what positive charge likes to do. Then, let's see, capacitors. I had already mentioned this, but Capacitance does not depend on charge or voltage, it just relates those two numbers. If you take the ratio of those two numbers, no matter how I vary the voltage, the charge will keep up, meaning more charge will flow onto the plates if I change the voltage. So the ratio of the two, the capacitance, doesn't change. You can change it if you change one of the three things we looked at here. The size of the plates, how close they are together, or if you put a dielectric in or take it out. Those are the things that can actually change capacitance. And dielectrics increase capacitance when you put them in. And then there were questions sort of like these, but I'll just I'll leave it at that, because I could say more, but again, some people haven't taken the quiz yet. All right. Have any questions popped up while I've been monologuing? If there are no other questions, then we will call it a day. Going once, going twice. Okay. I will see y'all on Monday. Enjoy your weekend, and I will have this up in a little bit. All right. Have a good one.